The Orion spacecraft's first successful launch marked the start of NASA's Artemis program, which will culminate with the construction of the Lunar Gateway in 2028. The Gateway is a planned international space station orbiting at the Earth-Moon L2 point and serving as a critical outpost for human missions to the Moon and beyond. The Gateway will be a hub for lunar exploration, providing a platform for astronauts to assemble spacecraft, conduct experiments, and test technologies needed for long-duration missions in deep space. Spacecraft can dock with the Gateway, allowing for crew transfers and resupply, and serving as a gateway to the Moon and beyond. It will be a crucial element in future human missions, providing a stepping stone for deeper space exploration. But what if there was a more cost-effective way to maintain a continuous human settlement on the Moon? Welcome to the world of cycler space stations. Cycler orbits build on the figure-8 free return trajectories used in the Apollo program, with the main difference being that they have constant periapsis and frequently visit the vicinity of two celestial bodies indefinitely. They can be classed by the number of petals in their orbits or by their orbital resonance. This 4-petal cloverleaf cycler has the advantage of proximity to the Earth-Moon L2 point, where a cycler or smaller taxis could dock at the Lunar Gateway. Cycler orbits can even connect to other planets in an interplanetary highway. The Aldrin cycler is the simplest possible circulating orbit between Earth and Mars. The size and scope of a mission to Mars entails massive propulsive requirements, which can be alleviated by the use of a cycler, especially on extended missions, with 50% launch cost reduction after 14 synodic periods compared to point-to-point missions. Critical architectural elements of a cycler space station include taxis to go from the planet's surface to low Earth orbit to rendezvous with the cycler, resupply modules to deliver supplies, the cycler vehicle itself, which is a habitable infrastructure linking low Earth orbit to low lunar or Martian orbit. This cycler consists of NASA deep space habitats, Orion light crew vehicles as taxis, and a solar electric propulsion system. The cost-effectiveness of cyclers is important because human settlement on the Moon or Mars will require frequent two-way traffic to and from Earth, and depending on the mass ratio between the taxis and the cycler, the overall delta-V cost of maneuvers to deliver taxis can be insignificant. A major feature of cycler orbits is the ability for escape maneuvers to be performed. In case of emergencies, the mission can be aborted and the crew can be returned to Earth safely, even in case of propulsive failure. Autonomous robotic systems have also been proposed for maintenance of cyclers in unmanned portions of their interplanetary journey. The ballistic trajectory of cyclers reduces fuel mass, which increases the allowable mass for crew comfort and safety, which are especially important to maintain mental, physical health, astronaut performance in long periods of occupancy. Crew systems could include artificial gravity by spinning sections of the space station to stave off effects of weightlessness on muscle and bone density. And outside of the Earth's protective magnetosphere, radiation shielding is also necessary to ensure the crew's safety. Food and water are likely to comprise a large portion of the mass of the cycler. This can be alleviated by testing the feasibility of bioregenerative systems or growing food in the station, making it self-sustaining in the long term. 50 years on from the first landing on the Moon, the future of space exploration looks just as bright. In a world of endless possibilities, cycler orbit space stations may yet be the key to unlocking the next frontier, be that the Moon, Mars, or beyond.